My name is Daud Ahmed. This is the second video of the series on graph neural networks. Let us talk about types of graphs. Graphs can be classified into two types on the basis of multiple criteria. The first criteria is the direction of edges. Remember that graphs model data in which the nodes represent the entities and the edges in the graph represent the relationships or the links between the nodes. For example, on LinkedIn, there is a user whose name is Ali, and there is a user whose name is Sarah. Sarah is being followed by Ali. Ali is following Sarah. So the edge is from Ali to Sarah. The edge represents following. The edge is not from Sarah to Ali. That is, the direction of the edge is from Ali to Sarah. It is a one directional edge. It is a directed graph. If, on the other hand, look at Facebook, Ali is a user and Sarah is another user. Ali is a friend of Sarah. So the edge represents friendship. But that means Sarah is also a friend of Ali. Friendship is mutual. If the relationship is mutual, that means the edge is undirected. So this is an undirected graph. The number of edges outgoing from a vertex in the case of directed graph is called the out degree of the directed graph. Out degree. And the number of edges incoming to a vertex is called the in degree of the graph. However, in the case of undirected graph, the number of edges connected to a graph is called the degree of the vertex. The number of edges connected to this node is the degree of this node. Suppose this is a graph, one node, third, and this one to this, and this one to this, and this one to this. The out degree of this node is 1 because one edge is outgoing. The out degree of this one is 2. 2 edges are outgoing. The in degree of this node is 2. 2 edges are incoming. And look at this one. Is undirected graph. The degree of this one is 2. Degree of this one is 2. Degree of this node is 2. The second criteria is the change in the properties of the graph over time. Sometimes in some graphs, the nodes and the edges, their properties remain intact, they never change. In citation graphs, the nodes are the papers, research papers. A paper may be on science, on Ebola virus, and a paper on AI. This paper cites this paper. So that is a citation graph. Neither the paper will ever change or the citation will ever change. They are published. But sometimes the properties change over time. For example, in communication graphs, person A communicates with person B. So it is a unidirectional graph. This is the edge represents whether person A is currently communicating with person B. Person A shuts off the call, the edges disappear. That is, the graph was dynamic. The third criteria is the nature of data, the nature of the nodes. Sometimes there is only one kind of node and one kind of edge. Suppose this is the Facebook graph with A being a user, B be the other user, C be the other user. A and B are friends, B and C are friends. All the nodes are users and all the edges are friendships. All edges are of the same kind, all nodes are of the same kind. So this is a homogeneous graph. What if we add a different kind of node? Let's say we add a different kind of node called post, and user C has made this post. User C writes this post. So we have a different kind of node as well as a different kind of edge. That means our new graph is now heterogeneous. It has multiple types of edges or nodes. Let's move to our next topic. Remember that this is all machine learning. If we are performing machine learning on graphs, then it is called graph learning. In graph learning, we can perform tasks at three different levels: the node level, the edge level, and the graph level. At the node level, we want to determine the label or the category of a node in the graph. For example, in a citation network, there are different papers represented by nodes. Paper A is citing paper B, while paper B is citing or referencing paper C. Paper A and paper B are both science papers. Is paper C a science paper or a math paper? What is its label? If we want to predict whether it is a science or math paper, then we are using machine learning to find the label of a node, and we are performing a task at the node level. Suppose these are different people. This is person A connected to person B, connected to person C, connected to person D. D is connected to B as well. Person A is a smoker and person B is not a smoker. Person D is not a smoker. Is person D a smoker? This is again a task at the node level. The second level is the edge level. We are determining relationships between nodes. For example, there are different people, different users signed up on a dating app. Do A and B make a good match? If yes, then there is an edge. Do B and C make a good match? If yes, then there is an edge. What about D? Shall there be an edge between D and A? Do D and A make a good match? If we want to find that out, then we are performing a task at the edge level. Is there such an edge or not? The third level is the graph level. Here, we are making predictions about the entire graph. For example, there is a molecule, a huge molecule. Instead of predicting something about a specific atom in the molecule or a specific bond between the atoms of the molecule, we are predicting something about the entire molecule, whether it can be an effective drug or not, whether it will bind to a receptor or not. So, such tasks are at the graph level. We have an embedding vector for each node u in the vertex set of the graph. Let V be the vertex set of the graph. Each node is represented by a u and belongs to this vertex set V. For each u, we have an embedding vector zu. Formally, there exists a zu for each u in V. Suppose this is a graph with 5 nodes A, B, C, D, and E, and each node has an embedding vector. Embedding vector of A is this one, 1, 2, 1, 7. That of B is this one. That of C is this one for D, and this one for E. An embedding vector is representing some information for its corresponding node. But we want to aggregate the information from each node to some information about the entire graph. This is called graph pooling. A pooling function takes as input the embedding vector of each node and produces an embedding vector of the entire graph. Denoted by this FP, this is the input to the function, this is the function, and this is the output. HG is an embedding of the entire graph. It represents something about the graph as a whole. This function works by simply summing up each of the embedding of each node, and it is then divided by a normalization term. Let me explain. This is a summation over the embedding vector of each node. That is, if this is the input graph, the summation would be 1 plus 3 plus 1 plus 1 plus 4. That is a 10. Then 2 plus 0 plus 3 plus 1 plus 3. That is a 4, 7. That is a 9. Then 1 plus 0 plus 3 plus 3 plus 2. That is a 9. Finally, 7 plus 1 plus 1 plus 1. That is a 10. We can see that the values are scaling up while the range of the node embeddings was from 0 to 4. These values are in the range of 9 and 10. So to scale them, we use this function. This means the number of nodes in the graph, which is 5. This function can be square of 5, under root of 5, or 5, or simply a 1. If it is a 5, our resulting graph embedding vector will be 2, 9 by 5, 9 by 5, and then at 2. This process is called graph pooling, and it is used to predict something or infer something about a graph. Recall the task of predicting whether a molecule can be an effective drug. The molecule is the entire graph, and we can use graph pooling on each of the atoms in the molecule to find an embedding vector for the entire graph and use that embedding vector to predict whether the molecule represented by the graph can be an effective drug or not.